All right, just two brief announcements before we start up. Collegiate Cancer Council is having their second general meeting on the 13th, which is, Tuesday, right after the exam. So you want to get your free food, and you can make your own sushi. You've got their meeting that you can go to. Yeah, as I said, see, make your own sushi. You know, I don't know if that means you actually get a fish and kill it, and then I believe it's actually they're probably going to have some sort of fun little project where you're doing that. And then the other one is the Society for Asian Scientists and Engineers are having their fourth general meeting next Thursday from 7 to 8:30. I guess MD Anderson is coming in to talk. I don't know who at MD Anderson, but if you're interested, I'll be posting these again. Well, I guess not for you all, since next Tuesday we have an exam. Oh, come on, it's not that bad. It's actually not going to be. Yeah, hey, at least you don't have to write another paper or something. No, not going to buy that. All right. Well, the good news is that I think this last part of what we're going to talk about today, this about respiration, is actually not terribly difficult. And really what we're going to be looking at is we're going to be looking at how we move the oxygen and the carbon dioxide in the blood and how we deliver it to the tissues and then return that material back to the lungs to be expelled. And so what we have here is just basically a nice little general model that we probably already understand, but just in case. Here we are at the alveolus. These are your cells that we're going to be delivering oxygen to and from where carbon dioxide is created. What happens is because of a pressure gradient, oxygen moves down its partial pressure into the blood, moves through the system, through the first pulmonary circuit, then through the heart, and then on through the systemic circulation to arrive at the tissue where it will be delivered down its partial pressure gradient from the systemic circulation into the cells. And because the cells are using up oxygen and producing carbon dioxide as a byproduct of glycolysis, or I shouldn't say glycolysis, but of glucose metabolism, we're going to produce carbon dioxide, which is building up, and so the partial pressure of carbon dioxide is low in the tissues, and so you move down your partial pressure gradient, move carbon dioxide into the system. It gets pumped to the pulmonary, through the systemic, up through the heart, and ultimately through the pulmonary circulation to move down its partial pressure gradient one more time so that it can be expelled. That's what we're going to talk about. It's all about pressure and partial pressures. All right? But there's some problems. That's it. Yeah, if you want to, that could be it. It really is. But there are some things you should first recognize. Is that atmospheric air, which has 760 millimeters of mercury on average, primarily nitrogen, oxygen, and then that small subset of noble gases and carbon dioxide and other pollutants and other things makes up that 760. But when you breathe in that air, remember, you have as a byproduct of your metabolism water, which is put into your lungs. And so when you breathe in, that atmospheric air mixes with that alveolar air, and so that water in your lungs, that is a vapor, makes up part of the pressure. And so your partial pressures for your gases just decreased by a percentage because of that presence of that water. So what I'm trying to show you here is atmospheric air versus inspired air. You can already see, and these are partial pressures, not total molecules or anything, that the partial pressure of oxygen decreases in the lungs just by virtue of you breathing in. All right? And then remember we talked about the alveolar dead space, or actually I should say alveolar dead space, but the dead space in the lungs, the bronchi and bronchioles, and so every time you breathe in and breathe out, there's a certain component, a certain proportion of air that's stuck inside your lungs, right? And so every time you breathe in, you take your fresh air and you're mixing it with stale air, which is kind of gross sounding, but it's there. And so again, we even drop our partial pressure even further. And then because oxygen is always going to be moving down its partial pressure gradient, which is lower, your partial pressure of oxygen is lower in the blood, regardless of whether you're breathing in and out or whether you're not breathing at all or expiring or inspiring at all, you always have oxygen moving into the blood. And so what we can say is that we have an average of partial pressure of about 100 millimeters of mercury. Now, if you go look at some textbooks, they'll say it's 104 millimeters of mercury, but who wants to work with a number that's so weird? 100 is nice and easy, all right? And so all of these things that we just described for oxygen is true for carbon dioxide as well. The difference is that instead of adding in oxygen into the alveolus, we're removing carbon dioxide. And so that partial pressure of carbon dioxide is roughly 40 millimeters of mercury inside the alveolus. And so already we have this nice little number that we can work with, and what we're going to do is we're going to use these numbers as a baseline to show you the movement of these gases. Am I going to ask you what the partial pressure of oxygen is in the lungs? No. It's not. It's 104. We said that a second ago. It is a weird number. That's why we don't talk about it. It's like our strange cousin. No, you don't need to know 104. You need to know 100. You don't need to know 40 or 36 or 44 or whatever the number actually is for carbon dioxide. I told you just need to understand the principles. Yes, ma'am. How much air can your lungs hold at one time? It's a lot. Yeah, what's your tidal volume? Well, about half a liter. About a half a liter, and that's in an average size male. I don't know what it is in females. I haven't even bothered checking. So, so no, the answer is no. Yeah, no. I mean, that's if you think about it, it's almost ridiculous that people require you to memorize those numbers, right? I mean, it's kind of good to know what it might be around, so that, when someone comes in and you do a measurement and it's like, well, you're only pushing in and out 100 mils of air, that might be an indicator that you're probably off by quite a bit, But should you know 500 and the guy's pumping out 498? Wait. No. Anyway, I'm going off on a tangent because I've had a long day. All right. Now, there are many things that influence the movement of gases, and a lot of these, other than partial pressure, and you know these already. You've learned these. This is based on Fick's law, right? I mean, the surface area becomes important, right? The more surface area you have, the greater probability of a gas molecule moving from the alveolus to the blood or vice versa, right? I mean, does that make sense? Sure. That's just diffusion. Well, that's what we're doing, is we're going to be diffusing, so yeah. So, how do we do this? How do we increase surface area? Well, let's open up more capillaries. If you open up more capillaries, you now have more blood perfusing through the area, so now you have a greater chance of gas exchange between the alveolus and the blood vessel. You can increase alveolar space, all right? And this is basically stretching. You do this through increased tidal volume, all right? So, in essence, what we're basically saying is, give me a nice big fat alveolus and give me as many blood vessels as I possibly can, as wide as possible, and that allows for the movement of gases back and forth. All right? So that's what our lungs are attempting to do. Even though we came up with those rules that say, how do we make sure that we hold on to oxygen? How do we make sure we get rid of carbon dioxide? Remember we talked about that last 2 slides of class, yes? Tuesday? Yeah. All right. The thickness. Thickness is obviously important. The thicker the barrier between this alveolus and this blood vessel is going to become an issue. Under normal circumstances, no. But let's think of some circumstances where it might. Inflammation would be good. Can you think of any sort of sicknesses or illnesses? See, I mean, you guys will know better than me. I'm just thinking pneumonia. You start producing water, and now you have a thicker barrier. It's just water. I mean, can oxygen and carbon dioxide dissolve in water? Yeah. But because you have to diffuse over a much larger distance now, that becomes a problem. It slows down the rate at which you can have gas exchange. And then we have this diffusion coefficient of gases. Now, have you guys, for those of you who are, well, I mean, you all are planning on some bigger things. When you guys took organic chemistry or P-Chem or even Chem, did you see those big giant fat books they have on the shelves, the CRCs? Yeah, and every now and then they make you go pick up that book and look up some horrible number that some poor Yahoo had to figure out a long time ago. You know what I'm talking about? Yeah, well, one of those numbers you can find in there is this diffusion coefficient of a gas. And what it is it basically tells you the degree of solubility of that gas in a particular substance. Usually it's water, but in this case we're going to be talking about with regard to lung tissues. And what it is that it's actually some sort of constant, and it's going to be related to its molecular weight. Now, interestingly, the diffusion coefficient for carbon dioxide is much, much larger than it is for oxygen, meaning that carbon dioxide moves very, very quickly down a gradient, whereas carbon dioxide is a little bit slower. It's about 20-fold difference between these two things. But what happens is because of the partial pressure gradients that we're going to be looking at, all right, so the partial pressure gradients, not just the partial pressures, the gradients, is going to balance this out. All right? Oh, please don't tell me you're going to give me the circle of death already. Why this will irritate me, just because I'm going to be sitting here looking at this for about 30 seconds before I freak out, is all day long I've been backing up my computer because I finally got a new computer to replace the 7-year-old one sitting on my desk. And this is what I got to watch all day long. This little tiny blue circle. I'm only backing up 160 gigabytes. So imagine, I've been backing up since 11 o'clock today, and it's still not done. No, it's okay. It's just doing this because it's confused. Now I'm just ready to fling this thing. See, what it's trying to do right now, I can't decide, is it actually open or is it actually closed? Curse you, computer. Ah, see, there you go. That wasn't hard. For what, a door stop? I mean, this thing is, literally, it's 7 years old. The chip in your phone is more powerful than the chip in this computer sitting on my desk. I am not kidding. This computer is so old that it had 1.5 gigabytes maximum memory. Yes, your little zip drive in your pocket has more RAM than my computer. Tell you what, you give me $5 and I'll let you haul it off. Wait, no, that made me stop. All right. Okay, so this thing is now just going to start ticking me off. All right, start my task manager. There we go. So, end it now. I know, this is what happens when you put your hands... Well, look at it this way. This is frustrating, but imagine if I have to get my whole lecture on with chalk when I have to sit there and talk at the board the whole time. You guys would just be frustrated. Yeah. I know, this ticks me off too. The good news is that this is not a hard lecture, so we'll be done pretty quick as soon as I get this back up. So basically, what we're going to be looking at, the big picture, which is the next slide, the big picture is looking at what we're trying to do. We're moving alveolar air into the blood. That blood serves as the middleman to drive that partial pressure. In other words, if you took out the blood for a moment, really all we're looking at is an exchange of gas between the alveolus and the tissue, right? The blood just serves as a middleman. And so what we have here is we said we have a partial pressure of oxygen of about 100 millimeters of mercury. What happens is down here, because we're burning through the oxygen, we have about a partial pressure of about 40 millimeters of mercury. And so you can see that partial pressure gradients between 100 minus 40 or 60 millimeters of mercury. And so what happens is the blood is serving as the middleman. As the blood arrives in the tissue, it has a partial pressure of about 40 millimeters of mercury. So oxygen is going to move down its partial pressure gradient until it equals equilibrium with the alveolus. Now, it's partially because of the rate at which the blood is moving through the capillaries, right? It slows down, and so oxygen can move very quickly into the blood until we saturate the blood with oxygen. And then now the blood moves away, and now it moves into the systemic circulation, or through the heart, down through the systemic circulation. Its partial pressure is going to be the same as is when it left the lungs. And then when it arrives in the tissue, because we don't have a lot of oxygen, we have a partial pressure of 40 millimeters of mercury, the oxygen starts leaving the blood to balance out. And it will continue leaving, because again, we're in a capillary system, and if blood is moving very slowly, that the partial pressure will ultimately match or become equal with the partial pressure of the tissues. And then that blood leaves, and lo and behold, it goes right back up. So really what we have here is we just have a middleman. And you can just think of it as just like any sort of problem that you've looked at, where you said, oh, look, here's my barrier. Over here I have 100 millimeters of mercury. Over here I have 40. What am I going to do? I'm just going to move down my gradient. The difference is we're putting blood as the middleman. All right? So what we say is that the net diffusion first occurs between the alveolus and the blood, and then between the blood and the tissues. And we're always going to be moving down that gradient all the way through with that middleman. And then the converse is true as well. Now here the partial pressure of carbon dioxide is higher. It's 46 millimeters of mercury. But the pressure in the blood is about 40 millimeters of mercury. And so what happens is carbon dioxide leaves a tissue and saturates the tissue where it becomes equal, 46 millimeters of mercury. And then when you travel away, the partial pressure of carbon dioxide, we said was 40 in the alveolus. And so the carbon dioxide leaves the blood until it balances out. And so the partial pressure becomes 40. And so what we've done here is we've just kept this balance over and over again, where the blood is serving as the middleman. And so we have a net diffusion between here and here with this as our middleman. And what we're looking at is 46 and then going downstream to our 40. That's all we're doing. This is coming in there so that we travel around. Now, how does this all occur? Well, we have to think, where is oxygen going, and then we're going to deal with carbon dioxide in just a moment. Now, I guess the easiest thing to do, I'll just leave it up here, and then if I have to draw it again, I will draw it out here. What you have to understand is that oxygen does not just get carried by hemoglobin. All right? And the partial pressure that we're talking about is actually the partial pressure of oxygen dissolved in the plasma. It's the liquid. Much like the carbonation in your drink is dissolved carbon dioxide, oxygen dissolves in the gas or in the blood as a gas and stays in there. All right? So when we're looking at that partial pressure of oxygen, we're saying that is actual oxygen sitting in the fluid of the blood. All right? But oxygen dissolved in the blood doesn't contribute all that much in terms of actual oxygen that you can actually use. It's very, very low. Now, this partial pressure, we just saw in the previous slide, is equal to the partial pressure in the alveolus. So, it's dependent on the partial pressure there. But because this is so low, and because you could not survive on the amount of oxygen dissolved in your blood, we have to go and get oxygen from someplace else. And really what we've done is we've created a portable oxygen ATM. What's our portable oxygen ATM? A red blood cell. And really, it's not the red blood cell itself, it's where we actually put the oxygen, which is hemoglobin. Right? What hemoglobin does, it allows us to carry more oxygen in the blood because of its ability to bind oxygen. Right? Now, hemoglobin will be considered saturated when we have 4 oxygens bound to the 4 hemes. All right, and this is real simple. You're 100% saturated because you have 4 oxygens bound to 4 hemes. So if I remove 1 oxygen, what is my saturation at this point? Yeah, see, this is real easy math. If I take away 2, 50%. If I take away 3, 25, and if I have none, 0% saturation. Now notice, we're dealing with some real simple math. Now, are we actually counting up all the red blood cells and counting up all the hemoglobin and then saying, okay, well, this one has 4, this one over here has 3. Are we doing that? No, we're just saying it's just a nice, simple general number. All right? And it's, even though we're talking about this as a percentage of saturation, what we have to understand is that the partial pressure of oxygen drives saturation. All right? And this is that whole law of mass action thing that I keep coming back to over and over again, that you keep going, oh, whatever, I don't care. Right? So, if my partial pressure of oxygen goes up and I have no oxygen on my hemoglobin, is that going to drive oxygen onto hemoglobin? What do you think? Yeah. Okay. And then by putting oxygen over here on my hemoglobin, that allows me to drive more oxygen into the blood. All right? And if I take oxygen away from the blood and lower my partial pressure, what do you think is going to happen to the oxygen on my hemoglobin? It's going to go and replace. That's right. And so what you're doing is you're basically balancing now between partial pressure and hemoglobin saturation. All right? So what we're saying here is as your partial pressure of oxygen increases, so does oxygen's ability to bind hemoglobin. And the converse is true as well. As it decreases, we're going to go in the opposite direction. So what you can do is you can think of this as a storage depot for oxygen. Yeah. We're going to deal with that in just a moment. But yes, that is going to be something that's going to favor the movement of oxygen even further. It is absolutely beneficial. And so the hemoglobin molecule is wonderful because not only does the partial pressure drive it, but every time an oxygen molecule binds to it, it favors the next one binding. It becomes additive. But I want you to think about this for a moment in terms of what we're trying to describe here. Over here on the left is a picture of blood without hemoglobin, blood without red blood cells. All right? Now, what we have here is we say, look, we have oxygen molecules sitting in the alveolus, and so it has a partial pressure of 100. The blood arriving in the alveolus has a partial pressure of 40, so those oxygen molecules are going to be driven down into the blood until you have equilibrium. So the partial pressures become equal. And so that is the natural state of things. And we said that that amount of oxygen is completely inappropriate or too low for you to actually survive. So if we throw in red blood cells that have hemoglobin in it, and I think each of these pictures are supposed to represent a red blood cell with a single hemoglobin in it. Okay, we know that's not true. Now you put the red blood cells in, and so every time you have a red blood cell that is empty, or the hemoglobin that's empty, as the partial pressure increases inside the blood, remember it's trying to get to 100, but now we have a driving force here inside the cell that's going to drive oxygen into the cell as well. See if I can do this even a little bit easier. I'm going to have to erase this garbage. Anyone care about rotational motion? It's far easier to think about it in terms of that it's not just moving oxygen from the alveolus and into the blood. So here's my alveolus. Here's my blood vessel. Here's my red blood cell. And over here is going to be my ultimate cell that I'm going to try to get to. All right. So oxygen comes in. Partial pressure of oxygen here favors the movement of oxygen out to the blood until there's equilibrium. Everyone's got that? All right. Is there a partial pressure of oxygen inside of a red blood cell? Should there be? What do you think? Yes. Right now, in our little model, is there any oxygen inside of our red blood cell? No. So we're going to have a partial pressure gradient that drives oxygen inside there. And so we're ultimately going to get a partial pressure of oxygen that's going to balance out with this, and this balances out with that. But then we also have our little hemoglobin molecule, which says as the partial pressure of oxygen goes up, that's going to favor the movement of oxygen onto the hemoglobin molecule, right? And so you're going to keep doing that. And so what you're really doing now, instead of just driving oxygen into the blood and just carrying it away, now you're carrying far more oxygen because you're constantly moving oxygen into these red blood cells so that it can bind up to our little oxygen bank. Remember how much we said? How many hemoglobin molecules per cell? Do you guys remember roughly? It was a lot. I don't think it was 10 to the 5th. I think it was 10 to the 9th, or it was 10 to the 500 times 10 to the 6th. It was, but you're right. It was a lot. 10 to the 5th is a lot. 5 times 10 to the 9th. That's not just a lot. That's a hell of a lot. right? And so no longer are you just carrying, I don't know, let's just make up a number, 1,000 oxygen molecules. Now you're carrying 5 times 10 to the 9th oxygen molecules per red blood cell, and then multiply by the number of red blood cells per mil, and next thing you know, you're not carrying 1,000, you're carrying thousands upon thousands upon thousands upon thousands of oxygen molecules. Not a bad trade-off here, is it? And all this is being driven by oxygen moving down gradients until you get here, where this gradient is going to keep favoring the movement of oxygen here because we keep getting rid of it. Ultimately, this will all become saturated. Partial pressure of oxygen inside the red blood cell will be 100 because we've basically saturated all our hemoglobin. We're 100% saturated in hemoglobin. So partial pressure becomes 100 here. Partial pressure becomes 100 here. Partial pressure stays 100 here. And by then, the blood moves on and goes into another tissue. Now, I'm sorry I can't draw this twice over here because it just takes forever. But we're going to keep it up here and we're going to come back to it because we're going to deal with carbon dioxide doing the exact same thing. And that's what this is trying to show you, is that it's basically saying I'm moving more and more oxygen into the blood because of the presence of red blood cells and because of the presence of hemoglobin. Now there's a relationship between oxygen and the percent saturation. And what this relationship does, it describes what oxygen does when you have low or high oxygen carrying capacity. All right? Now, notice what this is. This is not a linear association. This is a basic dissociation curve. And what you're seeing here is that when I have a partial pressure of 100 millimeters of mercury, my oxygen levels are, or my hemoglobin saturation levels are about 100%. All right? And then as my cell travels through the body and ultimately arrives in some tissue, does oxygen automatically come falling off the hemoglobin? What's it dependent upon? The partial pressure. Now, a normal resting cell, it has a partial pressure of about 40 millimeters of mercury. All right? And notice what happens here. Again, even at 40 millimeters of mercury, do we completely lose all our hemoglobin? No. No. In fact, we basically hold on to a lot of our oxygen. Right? We say, yeah, we're going to give you what you need. And this is where the dissociation curve becomes important, because what this shows you is as you get into activity or in areas where you're burning through your oxygen, all right, then that's when you're going to start seeing hemoglobin fall off. Look. I get rid of 2 hemoglobin or 2 oxygen molecules at, what is that, about 28 millimeters of mercury? It took me 60 millimeters of mercury just to get rid of 1, but to go from there to there, it's about 12 millimeters of mercury. Here, probably about another 10 millimeters of mercury. In other words, hemoglobin behaves in such a way that when your body needs oxygen, it will let go of oxygen. And when your body doesn't need oxygen, it's going to give you just enough to keep the cells happy. Now again, this is all driven first by what's happening with regard to the oxygen. Here we are at our cell once again. Our cell, our partial pressure, I should do this up here. Over here is 100. Over here, remember we said our partial pressure of oxygen is about 40 millimeters of mercury. All right? Now, in order to get oxygen inside the cell, that means oxygen has to be driven from the surrounding environment into the cell, right? Moving down its gradient. Right? So we have a partial pressure that favors the movement of oxygen into the cell. But as this pressure begins to drop, what are we going to do? Where are we going to get our oxygen from? How about from the blood? All right? And then when this partial pressure begins dropping, where are we going to get our oxygen from? From inside the red blood cell. And then from that red blood cell, that's the partial pressure, where do we replace that partial pressure from? The hemoglobin. Right? So in essence, what you have here is basically just kind of like a bucket chain, or chain gang, where you're just constantly moving things down gradients. All right? So you're replacing it from oxygen that you have available. Now, how much are we going to lose? Well, we're only moving one oxygen molecule when we have a partial pressure of 40, right? But if this slope becomes really, really steep, then we're going to have to start really removing oxygen from this hemoglobin. Does that make sense? And that's what this dissociation curve says. It says, when I really need a lot of oxygen, I'm going to start removing oxygen very, very quickly from my hemoglobin to replace the oxygen that's being consumed. Yes, sir. It exists everywhere in your body. That's right, because you have to balance everything out. Remember, it has to do with the law of mass action. Whenever we talk about law of mass balance or law of mass action, I know one is a chemical term and we use it loosely in biology. You know, we always talk about two states. Like when I refer to it, I always talk about enzymes or hormones, right? Where a hormone is bound up or it's not bound. And so there's a balance between those two states. Now, that's true for everything we talked about here. If you want to look at two states, we have oxygen here in the alveolus versus oxygen here in the blood, right? They're two different places. We talked about here in the blood and here inside the red blood cell. That's two places. Red blood cell versus hemoglobin. That's two things. But the problem is that these all exist or coexist together. So you have to balance everything along this line. That's correct. Right, because we're always, remember what I said, our partial pressure here is always 100. And so it's always going to be driving oxygen down its gradient. So as long as there's a gradient, oxygen is going to keep moving. And by binding things up here with hemoglobin, that's going to create the gradient for oxygen to move. Does that make sense? And then the converse is true. As I begin using oxygen in my chemical reactions, that's going to create a gradient that drives oxygen into the cell, which creates a gradient to drive oxygen out of the blood and into the surrounding tissues, which is going to drive or create a gradient that drives oxygen out of the red blood cell into the blood, which is then going to favor the movement of oxygen off of hemoglobin to replace all that. All right? Now, I know that sounds very long-winded and stuff, but when you think about it, or have you ever thought about oxygen movement in the blood? You usually think, okay, I've got red blood cells and I got blood and oxygen moves from the blood to the cell. The end. And it's not any of this middleman stuff. But this middleman stuff is important because without it, oxygen doesn't move. Right? Alveoli up here, little toe down there. You know, does this all make sense so far? Okay. Now, a lot of people look at these charts as dissociation curve, and then they start freaking out, going, "Oh my goodness, because there are other things that favor moving oxygen off of hemoglobin, not just the removal of oxygen." So even though we talked about those partial pressure gradients, I actually did pretty good in making it way over there. So you can see the mustard. Okay, cool. All right. It's not just oxygen unloading or oxygen partial pressures. There's other things. But we can make this really, really simple. You know, it's going to be pH, it's going to be temperature, and it's going to be the partial pressure of carbon dioxide. All three of these things favor the movement of oxygen off of hemoglobin. But what do all three of these things tell us? If you increase temperature in a tissue, what does that tell you about the tissue? It's working. It's metabolically active. If your pH begins to drop, what does it tell you about the tissue? How about metabolically active? I'm looking for the easy answer. All right? Metabolically active. And if your carbon dioxide levels start climbing, you are metabolically active. That's right. All three things tell you about metabolic activity. Right? So what these three graphs tell you is, look, here is your normal curve. But when you increase the partial pressure of carbon dioxide, what that's going to do is it's going to favor the unloading of oxygen faster than it normally would. How do you look at a graph like this? Simply say, look, I want to unload one molecule. Sorry, I can't do this real well because I want to unload one molecule of oxygen or off of hemoglobin. Well, with my partial pressure of carbon dioxide higher, I'm going to do that at a much, much higher partial pressure for oxygen. In other words, this favors the movement of oxygen off of hemoglobin in a environment that isn't where oxygen would normally be released. Right? I would normally be releasing oxygen from hemoglobin at 40 millimeters of mercury, but when my partial pressure of carbon dioxide is higher, 80 millimeters of mercury, I'm doing it now at about 55. Why? Because my cells tell me to. What if my temperatures are higher? Oh, we'll do 50 because 50 is easier. Right? 50 says, look, over here at about 25, 28, whatever that number is, that's when I normally release 2 oxygen molecules. But now, because I've increased the temperature inside the tissues, I'm doing it at a much, I've basically shift my curve to the right, and I'm releasing more oxygen at higher partial pressures. Does that make sense? So notice, is the body looking at the partial pressure of oxygen to determine when it's going to actually release? No. There are other factors involved. And it's basically saying, at what we would consider normal, something different is happening. Look what happens when we cool the body down. What happens in metabolic activity when you cool it down? It slows down. That's right. Look. At normal partial pressure of oxygen, you're still holding on to oxygen because your metabolic activity of the cell has slowed, and you do not need to be breaking down as much oxygen as you normally would. Yeah. Well, 20 degrees C is no, it's not too bad. Well, I'm sorry. I'm thinking of the room temperature. I was like, oh yeah, that's not too bad. Yeah. Yes, absolutely. You're absolutely right. Now I'm just sitting there thinking, no, that's almost room temperature. What do you say? No.
My question is this kind of a feed-forward mechanism that anticipates what metabolic needs are and keeps that?
Absolutely. That's absolutely the case. And then we have the fourth thing, which was mentioned on Tuesday, which is BPG. Right? And when you have biphosphoglycerate levels increase, that's going to basically reduce the affinity of hemoglobin towards oxygen, which causes oxygen to be released. All right? So in essence, we have different mechanisms to increase the rate at which we're going to release oxygen. And in essence, what we're doing is we're allowing the cells to tell the blood when it's time to give it oxygen. All right? It's like when you go shopping. When you go shopping, you go to the mall with a certain amount of money. I'm presuming the mall. With a certain amount of money in your pocket. Right? And then you go and you spend that money. And then when you need more money, what do? You go to the ATM. Difference is that you don't have to go find the ATM in some dark corner in the mall. You're carrying it in your pocket. It's a credit card. I know, it's a terrible analogy, but you get the point. All right, it's a way for you to basically say, or your cells to say, I need oxygen, give it to me now, and the body has it available. You don't have to rely on breathing harder and faster. It's there for you to get. Carbon dioxide, on the other hand, is slightly different. All right? Here, carbon dioxide is transported in 3 different ways. The first one is where we're actually physically dissolved, just like we saw with the oxygen. All right? So when we're talking partial pressure of carbon dioxide, that 40 millimeters of mercury, that is carbon dioxide dissolved in the blood and in all of these different places that we've just described. So we're going to have a partial pressure of carbon dioxide here. We're going to have a partial pressure of carbon dioxide there, partial pressure of carbon dioxide there, partial pressure of carbon dioxide in there, and these are all the same thing. All right? Difference is these numbers are going to be different. All right? And our arrows are going to be different. I know. I just made life loads of fun, but I didn't want to write it all out again. All right? And so here we have a partial pressure of carbon dioxide of 46. Over here, the partial pressure of carbon dioxide is 40 millimeters of mercury. And all points in between, as we're moving from the tissue, it's going to be 46. And then from here, 46. And it's going to drive it down this way. Okay? So that's how come we're driving in this direction. Because when we arrive, that's 40, and then we'll rise up to 46, so on and so forth. Moving in, move out, move out. So I don't need to explain the dissolved again, do I? I mean, you guys get it from the oxygen. It's just going in the opposite direction. Okay. Then we have a certain percentage of the carbon dioxide bound up to hemoglobin. All right. Now, this is going to be binding to the globin portion of hemoglobin. And what this does is it reduces the affinity of hemoglobin to oxygen. Or excuse me. Yeah, that's right. Hemoglobin's affinity towards oxygen. Every time carbon dioxide binds, it's basically going to again cause a conformational change. Oxygen is going to be kicked out, and now you're moving oxygen away. So you can see part of the reason why an increase in partial pressure of carbon dioxide can have an effect on the removal of oxygen. All right. But then the third way is that that carbon dioxide gets converted into bicarbonate. All right, HCO3. HCO3 or bicarbonate is more soluble in the blood than carbon dioxide is. And so what we can do is we can use a nice simple reaction using carbonic anhydrase as our enzyme of choice. Take carbon dioxide plus water, that converts it into carbonic acid, which then quickly dissociates into a proton and bicarbonate. Now what we've done here is now we have a chemical reaction that we can tilt one way or the other, right? So, this occurs inside the red blood cell. I'm going to just keep it right here. So, remember what we have, here's our dissolved carbon dioxide. It's out here in the blood. Some of it remains in the blood, but some of it comes inside the cell. And this is the partial pressure of carbon dioxide inside the cell. But because of the presence of carbonic anhydrase, we are now shifting or moving and removing carbon dioxide from the cell because we're basically converting it into a new molecule. And then now our bicarbonate levels are going to start building up inside the red blood cells. And once we reach equilibrium in this equation, then the equation stops, right? And so then we don't no more carbon dioxide would move inside the red blood cell. That means the carbon dioxide levels are going to become equilibrated with inside the red blood cell is going to be equilibrated with the surrounding blood, and then that will ultimately become equilibrated with the tissue. Okay? Everyone with me so far? It's the same concept that what we're dealing with hemoglobin. The difference is we're making bicarbonate instead of hemoglobin. But there's a problem. Do you guys see what the problem is? Is there a finite amount of space inside the red blood cell? Do you think that you could fill up the red blood cell pretty quickly with bicarbonate? Yeah. So if we want to keep this reaction going, what do we need to do? Let's get it out. That's right. So why don't we go ahead and just pump the bicarbonate out, and then by pumping the bicarbonate out, well, we're going to end up with a lot of extra protons. Well, that's no good. We need to balance that out. So we're going to go ahead and move chlorine inside our cells. That's called the chloride shift to balance out our protons. And so what we've done now is we're favoring the movement of bicarbonate out of the cell, and so now we have a way to move more carbon dioxide, because now our reaction is favored to continue moving in this direction because we're removing a component. Where do you think? Oh, come on. The picture even tells you. Where's it going? That's everything that I've drawn on the board. They do. Well, that's the acid-base balance. No? Where are you? Where is that light blue? It's a plasma. Right. So a lot of your carbon dioxide is sitting around as bicarbonate in your plasma. All right? Now, if I come back to our little picture here, remember we said that our carbon dioxide basically goes one of three ways. It contributes to the partial pressure of carbon dioxide inside the red blood cell, and also here. Okay, so I just equate these two things. You just have to have this in place so that you understand where the carbon dioxide is going. You bind it up here, right? So you make carboxyhemoglobin, right? And then you also make the bicarbonate through our chemical reaction. And then those levels will ultimately create it where you end up with balance, but we don't want balance. We want to get more carbon dioxide out of the cells, so we're going to pump our bicarbonate out here in the blood. And so now it's being transported. And what we've done is now we've created a shift to favor the movement of carbon dioxide out because, let's see if we can do this from backwards. As I remove bicarbonate from the red blood cell, that favors the movement of the reaction where carbon dioxide becomes bicarbonate. I'm not going to write the whole equation now, just bear with me, please. All right. So that carbon dioxide, remember, is being contributed here. So if every time I remove a carbon dioxide and make a bicarbonate, that's going to have an effect on dropping our partial pressure of carbon dioxide inside the red blood cell. Every time we remove a carbon dioxide from inside the red blood cell, we have to replace it from a carbon dioxide that was out here in the blood. And every time we remove a carbon dioxide here, we have to replace it with a carbon dioxide out here, which is replaced by the carbon dioxide being produced by the tissue. Right? It's a big giant slide. Or a big giant stairway, whichever way you want to look at it. All we're doing is we're just shifting things one way or shifting things the other. And then when you arrive out here in the lungs, what's the first carbon dioxide you're going to see go? Remember, the partial pressure here is 40. Partial pressure out here in the blood is 46. Where does the carbon dioxide come from first to go inside the alveolus? From the plasma. Now, I just noticed something that I left out. Would we expect to see carbon dioxide in that little space too? In the interstitial space? Yeah. When we're going this way, do you expect to see oxygen out here? Yes. All right. You get the point, though. So the first carbon dioxide we're going to see is this. So it leaves. And when the carbon dioxide leaves there, where are we going to replace it with? Carbon dioxide that's inside the red blood cell. And when we remove a carbon dioxide from the red blood cell, how do we replace that? Reverse the reaction, right? Just take bicarbonate, make carbon dioxide again. And every time you remove a bicarbonate here, how do you replace that bicarbonate? Take it out from the blood. Do you see? It's just moving things around. Even though it looks all scary and complicated, what have we done? Remember that first slide I showed you before we started talking? And I know I have two questions here. Before we started talking everything, I had a picture of the alveoli, I had a picture of the cells, and I said, who's playing the middleman? The blood. All we're doing is we're really moving something from here to here. There's just a lot of little steps in between. Okay? And we're trying to balance them out. So we'll go here, and then I'll go over there. Yes, they will move out, but really the number of protons that are actually found in the blood is relatively small relative to the number of bicarbonate. I cannot remember the exact number, but it's something like 100,000 to 1. So the effect of a single proton in terms of the pH on the blood is significant. The effect of a single bicarbonate molecule on the blood, grossly insignificant. And we're going to talk about how to maintain that acid-base balance after the exam when we talk about the kidneys, because one of the roles the kidney plays is in maintaining that balance. Yes. Well, so even though you'd increase the quantity or the amount of hydrochloric acid inside the red blood cell, all right, that's not going to have a major effect on the actual acid base. And actually what you're doing is you're just waiting to come over here into the lungs so you can have all those reverse reactions, and then you do the chloride shift in reverse. So chlorine, see it over here, chlorine goes out, hydrogen stays inside. Why do you need the hydrogen inside? Well, so that you can do the reverse reaction. So you can get your carbon dioxide and water back. All right? Yeah.
So bicarb's job is a blood buffering agent and kind of ancillary cap.
Chicken and egg question. I don't know which came first. You want to know what the Haldane effect is? You sure? Actually, Haldane effect is really simple. There's actually two different effects, and I actually have thrown one out. There's one that's called the Haldane effect, one that's called the Bohr effect. And they can become very confusing because they're very closely related. All right? The Haldane effect is essentially is the effect of protons binding to hemoglobin. All right? They don't just sit there floating around. Some of them actually bind up to the hemoglobin. And when they bind to the hemoglobin, they drive or favor the movement of this reaction to the right. Right? So every time you get rid of a hydrogen, you're going to want to move the reaction this way to replace the hydrogen. You have imbalance, right? Think about it like this. So here's your equation, right? You have a lot of carbon dioxide, you have a lot of water, you have no hydrogen, you have no bicarbonate. As you start making the bicarbonate and the hydrogen, what happens to the equation? You're going to start reaching equilibrium. But if I take away a hydrogen, what's that going to do? It's going to tilt it again. I should do it this way since this would be the right. Right? This is the stuff in chemistry that everyone goes, huh? Because what you guys are not, for those of you who are confused, the thing that you're not seeing here is that when hydrogen binds hemoglobin, do we still have hemoglobin? No. Do we still have hydrogen? No. What do we have? A brand new molecule. Right? You know, it actually favors or it promotes hemoglobin to release oxygen, and in doing so, drives a reaction to the right. No. Nope. And it doesn't bind in the same place that oxygen does. So it's not a competitor with oxygen. It just favors hemoglobin's ability to release oxygen, and it favors, once that happens, it favors the movement of carbon dioxide. Right, and drives a reaction so that you have a way to transport carbon dioxide. That's the Haldane effect, right? I mean, look at it this way, all right? If I have a whole bunch of hydrogens that I'm putting up, all right, why do you have a whole bunch of hydrogens? Well, that's a result of an increase in partial pressure of carbon dioxide, all right? Well, as the hydrogens bind up to the hemoglobin, it's going to cause the oxygen to bind off, so you end up with basically a free hemoglobin that can now bind up to carbon dioxide, and when it binds up to carbon dioxide, that's going to shift or favor the reaction to make another hydrogen. All right? It's kind of a big giant circle, which is why I tried to draw it like this. Am I making sense or no? Yeah? No? Yeah? No? Kind of? Huh? I'm crystal clear? Oh, I love that. I'm going to have to get that on a poster. Put it on my door. I could do that with people. No, we don't want to do that one. No. So that's the Haldane effect. The Bohr effect just does it with carbon dioxide. Every time a carbon dioxide binds, it favors the movement of oxygen off of, or every time you produce carbon dioxide, it favors the movement of oxygen off of hemoglobin, which allows it to bind carbon dioxide, so on and so forth. So it's just basically saying, whenever you have lots of carbon dioxide or lots of hydrogen, that's going to push oxygen off of hemoglobin so that you can drive more carbon dioxide into the red blood cell so you can carry it away. That's all it is. And if you try to make it more complicated than that, even though I try to make it more complicated than that, I didn't try to. It's just I'm looking at faces, and that's all we're basically saying is that these factors promote the removal of oxygen so that we can carry carbon dioxide away. That's all it is. Yes. Yeah. What kind of molecule is it? If I add a proton to it, it's still hemoglobin. What kind of hemoglobin? Huh? Protonated. All right. If I add carbon dioxide to it, what is my hemoglobin? Is it still hemoglobin? No, it's carboxyhemoglobin. If I add oxygen to hemoglobin, it is oxyhemoglobin. All right. I know this is it's almost unfair to say it like that, but I mean that's really what you do, right? You've changed the molecule by changing something to it. It becomes something new. All right? Let me ask you this. Is that molecule the same thing as that? No. I mean, it's not a trick question. No.
Think of it in terms of like a conjugate acid or conjugate base.
Except that if I have 10 of these and I have one of these, what's going to happen is my reaction is going to move in this direction until I get balance. And every time I remove one of those, It's going to keep trying to make it till there is equilibrium. So they're not the same thing. That's what I'm trying to get at, right? All right, now before we stop talking about these things that seems kind of scary, it shouldn't be. Don't be scared. I see that look. She's good. I'm going to be studying Saturday and Sunday. No. It should not be scaring you. All right. It should be like you should be thinking, I understand the basic chemistry behind this, and if I have a slope, I move down the slope. All right. That's all it is. Trust me, it's not that hard. In the exam, you're going to be like, well, where are these hard questions coming from? They're not. There's none there. It's an easy exam. Yes. That's why I say it's like an oxygen bank. Or, in the case of carbon dioxide, it's a carboxyhemoglobin bank. No, it's a carbon dioxide bank. All right? But where's your better carbon dioxide bank? Between the blood and hemoglobin, which is the better carbon dioxide bank? Hemoglobin. And how do we store hemoglobin in our carbon dioxide bank? As bicarbonate. The end. And then when it comes time to get rid of the carbon dioxide, we have to just convert bicarbonate back into carbon dioxide. Do you think this reaction takes long? No. It's very quick. That's all we're doing. It's just acting as the middleman. All right. Now, we're down to the last couple slides. You're thinking, my goodness, I'll be able to get on the highway in the dark and all that traffic early. You know, if I kept you here to 5:30, it'd get home faster. Or at least, probably about the same amount of time, you just wouldn't be as frustrated. But we'll see. All right. So we actually have respiratory centers that are actually located within the brainstem, and their job is to act as your metronome. Right? Your breathing metronome. It's your rhythmic breathing patterns. Now, in the brainstem, these centers are under voluntary control. Right? I mean, you can read. Everyone, hold your breath. Breathe fast. See? Voluntary control. You can do that. But we can also look at it in terms of what's going on in terms of this rhythmic activity and seeing what types of controls. We have those kind of controls that are responsible for alternating the patterns of inspiration and expiration. So that would be regulating your tidal volume. Those that regulate your magnitude to meet your needs. And then those that modify your breathing patterns to serve other needs. The good news is we're going to try to keep this simple. All right. So in the medulla, we have two respiratory centers. All right. We have what is referred to as the dorsal respiratory group and the ventral respiratory group. Actually, I think in the new textbook, it's actually, I think they've lumped them together at this point. I'm not 100% certain, but we're going to go with this right now. All right. Now, the dorsal group contains inspiratory neurons. And what they do is they basically fire, and they keep increasing the rate at which they fire, which causes you to... And then when they stop firing, it causes the muscles in the chest to relax. And you exhale. All right? So in other words, what they do is they create the force that causes your thoracic cage to expand during inspiration. And when they stop firing, there's no more contraction of the muscles. No contraction of the muscles. Your muscles relax, your chest or not collapses, but goes back to its original shape, and you breathe out. That's exactly right. That's it. Kind of cool. Now we have the ventral respiratory group, which have both inspiratory and expiratory neurons. All right? And so when you increase your activity, these are the ones that begin firing. All right? And then similarly, the expiratory ones are going to start firing when you need to force expiration. So can you think of a circumstance where you might see the ventral group come into play? Scuba diving, okay. Anyone ever been late for class? Never. No, when you're running across campus, right? You have to force inspiration and force expiration. This would be the ventral group. And then we have another group of cells called the pre-Botzinger complex, all right? And these have pacemaker activity. All right, that's what that is right there. All right, and so they're the ones that actually kind of say, all right, this is the rate at which you're going to begin firing. All right, and so they're the one that kind of meters the activity. No, that's going to be the special circumstance ones. So remember we said the three groups, ones that are for inspiring, one for increasing, decreasing, and then the third is special needs. So that, or not, I should say, the second one is magnitude, the third one is special needs. So coughing would be the special need. It's like, wait a second, you have something stuck in your throat, time to remove. And so it's going to override the normal activity. All right? And then we have the pontine group, which is this one up here, and we have neurons that act negatively on the inspiratory group, and so this acts to shorten inspiration. And then you have those that act as a negative factor, basically to prevent them from being turned off, and so what we have here is something that lengthens. And so what you can really think here is that the pontine group modulates the activity that's occurring in the medulla. All right. That's how just these are modulatory. Now, what your body does when it decides have you ever done that? All right. Have you ever done just a random sigh for no reason? Yeah. That actually has to do with actually balancing out your acids and bases, but I just wanted to see if you guys had ever done that. Your body doesn't really monitor partial pressures of oxygen. Your body doesn't say, it's time to breathe in because the oxygen levels are kind of low in your body. It's time to do that. No, it does not. In fact, the only time that we actually care about the partial pressure of oxygen in the blood is when you get down to life-threatening levels. So we are detecting it, but they play almost no role in determining whether or not you're actually going to be breathing in. All right? So imagine you've had those contests when you were a kid, see who can hold the breath their longest. You know, it's not like because you didn't have oxygen. I mean, that was the end of the contest. Right? Right? So the partial pressure of oxygen is going to be measured in the carotid arteries, going to be measured here in the aortic arch, and there are specific chemoreceptors that are responsible for measuring carbon dioxide levels, oxygen levels, so on and so forth. So oxygen levels, not so important. Partial pressure of oxygen, not so important. In the periphery, we do have receptors that look at carbon dioxide. And so we can stimulate them with the partial pressure of carbon dioxide and do so slightly better than we would oxygen. In other words, as the carbon dioxide levels begin to build up in your blood, the chemoreceptors would start going, hey, wait a second, we got an issue here. All right? So it's not about the oxygen, it's about carbon dioxide. All right? Now, in the periphery, not such a big deal. It's in the medulla where it does become a big deal, which kind of makes sense because what's in the medulla? Breathing control center. Now, it's not really so much the carbon dioxide, but you do have chemoreceptors that are detecting carbon dioxide.
So, I mean, as a result of all those reactions, what she was talking about earlier, we have the level of protons received in blood with the respiratory acidosis, or alkalosis, or whatever. That's what kicks on to the turn off gas that.
You're absolutely right. And that's primarily regulated through, well, a lot of it is regulated through the kidney. So that extra acidosis, we're going to talk about it in the kidney. The protons that are extra, we can off-gas quite a bit of it, but the rest of it is taken care of by the kidney as it's basically. Well, it's actually not the urea itself. It's actually, yes. Yes, yeah. So, blood-brain barrier obviously prevents material from crossing into the medulla, but the carbon dioxide has no issue. It can readily diffuse. We already saw it had a high diffusion coefficient, so it just goes wherever it wants to go. All right. But we also know and this is what I was trying to describe earlier in terms of the tissues, your partial pressure of carbon dioxide in the arteries should be equal to the partial pressure of the carbon dioxide in your extracellular fluid in your brain, just by virtue of pressure gradients, right? You're going to see balance, right? And remember, your brain tissue is basically burning through oxygen, and so it's producing carbon dioxide, so that's where these two values basically come into play. But the other thing to remember is that carbonic anhydrase is one of these things that's found all over the place. And so really what happens is that carbon dioxide gets converted into bicarbonate. For example, here in the cerebral spinal fluid. I presume that's how they're trying to say it here. It's done in all sorts of tissues. I mean, we haven't done digestive in here either. Yeah, we're going to see it's done in the digestive system. We're going to see it's done in the renal system. Carbonic anhydrase is this, it's in the red blood cell. It's all over the place. And so this is how you get rid of carbon dioxide. You just turn it into bicarbonate. And so it's this proton that your body actually cares about. And so when it starts looking or sees an increase in acidity, or I should say drop in your pH, what it's going to do is that's the signal to say it's time to inspire, get more oxygen into the body, because if these levels are getting up, that means the oxygen levels must be going down. All right? So, in essence, it's this proton that makes the biggest deal. Now, I usually like to turn off my things so all those people who haven't showed up to class don't hear this, but I'll just tell everybody. There's always a question on the test that says, which is most important? All right? Oxygen, carbon dioxide, or protons? And it will usually tell you in the periphery, whatnot. So the most important thing is always protons. All right? Followed by where? In the brain. Followed by followed by carbon dioxide in the blood in the periphery, followed by oxygen in the periphery. So that's the level of importance. So if you see a question that doesn't have protons in it, your answer is going to be CO2 in the brain. See, it's simple. It's just which one's more important? Yes. In terms of higher or lower. So highest, let's just do this again. Let's see if there's something over here. Just remember, after you graduate, you become wealthy physicians, endow the school with millions of dollars, so I don't have to use chalk. Okay. Proton concentration in the brain is greater than partial pressure of carbon dioxide where? In the brain, which is more important than periphery, which is more important than oxygen. There you go. Easy enough. This is greater than that, which is greater than that, which is greater than that. Yes. 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 Yeah. That's exactly what it is. All right. There is one caveat though in all of this. And it's not really a caveat. It's just so if your partial pressure of carbon dioxide gets really, really high, that's actually a signal to your brain to say, you know what? All that extra breathing that you're doing isn't working. In fact, you're probably breathing in carbon dioxide. So we're just going to go ahead and stop doing that now. Because it's bad. So really that's what it says. You depress the respiratory neurons when you get really, really, really high partial pressure of carbon dioxide. So don't go play in refrigerators. I'm sure your parents never told you not to play in a refrigerator. Did they? Do you know why they used to tell you not to do that? Can you lock yourself inside a refrigerator? Old ones.
Only if there's cheesecake.
Yeah. No, it's actually